talking about the absolute Galois group of fields. So everybody probably in this room knows what that is. So if you have a field, you can associate to its absolute Galois group, which is just the Galois group of the separable closure, K bar over K. And today all fields will be of characteristic 0, so you may think of it as K bar being the algebraic closure as well. That makes no difference. It's in a natural way a profinite group, the inverse limit of all finite Galois extensions realizable over Q. And when I talk about isomorphisms between absolute Galois groups, this is always meant in the sense of profinite groups, so together with topology. So we are not only interested in finding what these groups are, but also what they say about the arithmetic of the underlying field, and I will focus on that. So to give an example, obviously if the absolute Galois group is trivial, then that is the same as saying that the field is separably closed, or algebraically closed in characteristic 0. Another example is if the absolute Galois group has just 2 elements, so it's the absolute Galois group of the reals, then that field is a real closed field. That is classical Artin-Schreier. Then field K is elementarily equivalent to the reals, which means it's a real closed field. So, for example, you may have K to be the real algebraic numbers. They are an example. Or you may take K to be the field of generalized series. So this is like Laurent series over the reals, except that the exponents are not integers, but rational numbers in the additive group of rational numbers. So they all are real closed fields and have that same Galois group. P-adic analog we have as well. If the absolute Galois group is isomorphic to that of the p-adics, then the field is elementarily equivalent to the p-adics. And again, we have the same kind of example. You can look at the algebraic p-adic numbers. Or you know that by QP alt, which is just QP intersect Q bar. Or likewise, you can do a similar construction here. Form a power series with exponents in Q and coefficients in Q. They all have the same Galois group. And the big question is, what about fields with the absolute Galois group of Q? And there's a conjecture I would like, let me call it Galois conjecture. It's not that Galois has conjectured it, but Galois conjecture over Q, if you wish. So for that Galois conjecture, I consider an arbitrary field K, so K any field. Then the claim is that if the Galois group of K is isomorphic in the profinite sense to the absolute Galois group of Q, then K admits a Hanselian valuation with divisible value group and residue field precisely Q. So then K admits a Hanselian valuation V with value group, which I denote by VK, as has been standard in a couple of talks now, divisible and residue field denoted by KV, precisely Q. And of course I allow the trivial valuation here because obviously K equals Q is a good example for this. So yeah.
Yeah, so this isomorphic in the profinite sense, does that mean both topologically and sort of as groups?
Exactly, precisely. So the converse of this conjecture is sort of obviously true for people who have seen Galois theory of valued fields. So it's easy that when you have a field with these properties, then its absolute Galois group is isomorphic to that of Q. And I mean here in the case of reals and QP, the Galois group determines the full elementary theory of the field. That is not quite the case here. Here you have that the Galois group allows two elementary classes, namely either K is elementarily equivalent to Q, for example, if it is equal to Q, if the valuation is trivial, or K is elementarily equivalent to the field Q double brackets Q. So again, the generalized Laurent series field now with coefficients in Q and exponents in the additive order the being group of rationals. So that means this Galois group captures two elementary classes, so to speak. A consequence of this, which is perhaps a bit of a surprise, well, it's a conjecture, so conjectures may have very interesting consequences if they are false, but let's suppose it's true, this conjecture, then a consequence of that is that we have a surprising characterization of the field of rational numbers. This is the morning of rational numbers, I have observed. So the consequence is that if you take an arbitrary field K, then K is Q, if and only if the absolute Galois group is that of Q. And K is not large. A large field is a field which, that has occurred earlier in the week already, when it has a rational point for a smooth algebraic variety over K, it has infinitely many. Sometimes people call it ample. Or another, in fact, a single example of this non-largeness is good enough. Namely, GK is isomorphic to GQ, and for all x, y in K, you have that the Fermat curve, x to the 4 plus y to the 4 equals 1, only has trivial solutions. So, the rational numbers are uniquely determined by their absolute Galois group and that tiny bit of Fermat, which actually Fermat has proved himself. So that's why I'm putting down this equation rather than for higher n. So really may say the rational numbers are Galois plus Fermat, or plus a small portion of Fermat. Okay, when I gave my talk in the summer in Banyuls, where some of you have been, again my apologies for that, I thought I had proved that conjecture. Unfortunately, there was a gap in my proof which I couldn't close until today. I'm still
Maybe by the end of the talk.
Maybe by the end of the talk. Maybe you have brilliant ideas to tell me, and then in the rest of the week I can prove that. But as it is at the moment, we don't have proof for that conjecture, but we can say a lot regardless. So let me start with the first chapter, which is sort of exploiting the local structure, which is encoded in GQ. And so for this we assume that we have an arbitrary field K and an isomorphism, we call it phi, topological and group isomorphism to the absolute Galois group of Q. Then we have a few observations, some of them very simple. The first one is characteristic of K must be 0, and there is a unique ordering on Q, on K, which makes it an ordered field. The ordering is of course compatible with the field of operation simply because the absolute Galois group has involutions, that means subgroups of size 2. We know they come from real closed fields, and then of course you can restrict that ordering on that fixed field, and you get an ordering on your field K. The uniqueness comes from the fact that any two involutions in the absolute Galois group of Q are conjugate. This is simply because Q has an isomorphism unique real closure with respect to its unique ordering. So that's easy. But there is a p-adic analog. So for each prime p, and I denote the set of primes by this, there is a unique p-adic variation, Vp, p-adic just meaning residue field Fp and value group a Z group, elementary equivalent to the integers and value of p being minimum positive with Henselization being the field which I call Kp, which is the fixed field of, now I have my phi here, I can take the pre-image of the subgroup of GQ, which corresponds to the Henselization of Q with respect to its p-adic valuation, which is QP Alge in the terminology over here. So I take this pre-image. Let me draw a picture, and then you will see what I mean. The picture is this. Here we have K, and here we have Q, and we are looking at the corresponding K bar and Q bar, and we are looking at the corresponding Galois group over K respectively Q, so it's trivial here. Then here you have a subfield QP algebraic inside the algebraic numbers, and here you have this Kp, and this Kp is obtained from, I mean, here you just have the absolute Galois group of QP algebraic, and I can omit the algebraic because then they have the same absolute Galois group, QP and QP algebraic. So down here I have K and Q, which corresponds, of course, to the Galois group GQ here and the group GK there, and we have this isomorphism given from the outset. And of course, that I can take the pre-image of this group here, and this gives me my GKP. So this isomorphism gives an isomorphism between those two. And because we have this condition here, that if the group of a field is that of a p-adic field, it is p-adically closed, you get that these guys are elementarily equivalent. So this comes just from the fact here. So there is a p-adic valuation, and of course I can restrict that down to K, that gives me a p-adic valuation. Here, again, unique up to unique because the Henselization is unique because all those GQP algebraic subgroups in GQ are conjugate. So that gives you the uniqueness, and the Henselization is precisely this. So we already know quite a bit of local structure on K, ordering and all those p-adic valuations coming from the Galois data. And we can exploit that a bit more to see that if you have, for example, a Galois extension, L over K, a Galois extension, finite, say, then the absolute Galois group of K in fact sees all the ramification and the behavior of how those VPs split or not split when you go from K to L. So that is to say, GK, the Galois group of K, sees all the ramification and inertia degrees. So all, let me call them EVP of L over K, so this is all the ramification indices with respect to the p-adic valuation VP, and all the inertia degrees with respect to VP L over K. And the reason is that the absolute ramification subgroups and inertia subgroups of the p-adics are characterized in purely group theoretic terms. You can give purely group theoretic description of those, and they pass from here to there. And then you restrict down to your Galois extension L over K. So all the ramification delta of all data of all the VPs are seen by you. And in particular, you get something, you get a lot of arithmetic of algebraic number theory also being true in K. For example, you get geometry of density theorem. And K satisfies in this extension L over K geometry. So if you don't know what that means, never mind. For an example, it just says that if your degree L over K is 2, then half the primes are split completely and the other ones don't. So there's only finite ramification. That's again a consequence of this GK seeing all the ramification data. So for example, if the degree is 2, what that means is that the set of primes for which the local extension L Kp over Kp also has degree 2, I mean it can have degree 1 or 2 only, that this set of primes is in fact a nice set of Dirichlet density a half. This is an example of Chebotarev density theorem if you haven't seen it. So that is all encoded in the Galois group. And so what we have as a consequence of that is that we are starting with an arbitrary isomorphism from GK to GQ, but in fact, as a consequence, you get, say, as a lemma, you get that if GK is isomorphic to GQ, then we already know Q is a subfield, so it makes sense to talk about the restriction map from the absolute Galois group of K to the absolute Galois group of Q. And the claim is that restriction map, the natural restriction map from GK onto GQ, is already an isomorphism. Why is that? Essentially because this last bit here tells you that for any fixed n, there are only finitely many extensions of degree, at most n, of K, which ramify in primes only smaller or equal to n. That is part of what you have learned in algebraic number theory, that because all these data are encoded in GK, they carry over to the K side. So there are only finitely many extensions of K of fixed degree and of bounded ramification. And so take the compositum of all those for a given n, that gives you a certain finite Galois extension of K, which has a pendant on the Q side, and we know that all of Q bar is exhausted by these if n grows, likewise for the K's, and so this is the crucial thing to see why in fact the restriction map is already an isomorphism. And as a consequence of that, you have that if you look at K modulo nth powers, there is an isomorphism of Q modulo nth powers to K modulo nth powers, coming from this. So you have for each n, you also have that if you look at multiplicative group of Q modulo nth powers, and of course there's a natural map into the corresponding quotient over K, and that is again an isomorphism for each n, which is a fairly strong arithmetic statement for K. Now, what we get from this is, as a consequence, not the thing which is as strong as here, that Q is uniquely determined by Galois plus that statement on the Fermat curve of degree 4, but a very similar statement. So let me put that just underneath here, corollary, K any field, and then K is equal to Q, if and only if, and now I try to mimic as close as possible a statement as over there, GK is isomorphic to GQ, which by what we know now is the same as saying that the restriction map is an isomorphism. And if you look at the K rational points on the curve C parameterized by A, I'll say that in a second what that is, over K, so the K rational points on that curve are the same as those of over Q for all, say, non-zero natural numbers n, they say square free, doesn't matter. So what is the curve CA? CA is simply the curve x to the 4 plus y to the 4 equals A. So it doesn't suffice to look at a single curve, but this one parameter family of curves, it suffices that K has no more rational points on each of those than over Q. This suffices, together with the information of the absolute Galois group, that your field K is actually pinned down as all of Q. So that is a little corollary to that here. Okay, so far for the local structure. Questions?
Which corollary follows from the lemma above?
It follows from the lemma above because if you look at arbitrary elements x and y in K, then x to the 4 plus y to the 4 is just a number in K that has modulo 4th powers, a unique representative in Q. And this will be your A here, and you have to do a bit of more in order to show the full thing, but that is not hard to see directly from the definition. Yeah?
I'm not super familiar with the Galois or Q bar over Q. Does its explicit properties actually matter here, or are we just concerned with things that sort of externally we know have the same Galois?
We are working just with the fact that we know all these QPs, and of course we know all the ramification stuff about which you learn in algebraic number theory. So much you have to know. Of course, we have no idea what GQ is.
Okay.
I'm not asking this question here. We don't even know whether a very finite group occurs as a quotient of GQ, inverse Galois problem, wide open. I'm really interested in the direction from right to left. What does the Galois group know about the field rather than what is the Galois group given the field?
But you've already used some heavy arithmetic, classic law, so the Minkowski theorem, right? So that.
Yeah, sure. Of course, I should say from all of this, you get immediately, as you say, Hasse-Minkowski for K. You get immediately Kronecker-Weber for K.
No, I meant that you used a structure theory of the absolute Galois group, that you detected all these inertia groups, and then you can say what are the finite quotients which are unramified outside a finite set, for a certain degree, and then we know something about this. It says something about how complicated the group is, not really in terms of this and that group occurs.
You're right.
It's information about this absolute Galois group.
I used all the local information encoded in GQ and how it shows in finite quotients. Yes, all of that is definitely
global information. This Minkowski theorem that this is finite is global.
Yeah, no, definitely. Local information plus how they play together globally. Absolutely. No, that much information I definitely use about Q. But it's not that we have a restriction of GQ in terms of generating regulations or anything of that sort. And, that's totally agree.
Is your lemma then also an if and only if?
Well, yes. If the restriction is an isomorphism, then this is the isomorphism.
Oh yeah, that's
Yeah.
Oh yeah, there's no other, because all automorphisms of Gal Q are inner.
Yes, it also tells you that there's not much choice of your original phi. The phi is unique up to, by a theorem, a deep theorem of Ita, is unique is a unique isomorphism up to inner automorphisms of GQ. We know there are no other automorphisms of GQ other than inner automorphisms. So that tells you that this phi is almost fixed. Okay, now
Can I ask, how do you get Hausdorff-Minkowski from I don't see how, I mean, Hausdorff-Minkowski is a statement about rational points.
you have to say,
How do you understand rational points in terms of...
well, you encode stuff about H2, and then you get all the quadratic form theory sort of carried over using the Brauer group.
Okay.
It's not completely straightforward.
Okay.
You have to do a bit of work.
And,
Yeah.
and a similar, well, for these statements, but in the corollary, I didn't, well, maybe you don't want to explain it now, but I didn't follow it either.
So,
Maybe you don't want to explain it now.
yeah, I'll say something towards the end, perhaps, in this direction. The point is, if you have for some of these, x to the 4 plus y to the 4 equals something, you will have, if you choose x and y to be transcendental over q. This is a variety which has only finitely many points over q, but you definitely get a transcendental extra point if you're not q. That is. Anyway, we can discuss that later. Okay, now this was talking about arbitrary fields. Now I would like to reduce the conjecture to the special case of transcendence degree 1. So let me say how that goes. Reduction to transcendence degree k over q equals 1. I should say, of course, there's also the case transcendence degree k over q equals 0, if k is algebraic over q. But then, because we know if you have that isomorphism, the restriction map is also an isomorphism. But if you have an algebraic extension of q such that the restriction map is an isomorphism, then k cannot be anything else but q. So this does the transcendence degree 0 case. But now the interesting thing is, how do I reduce the general case to transcendence degree 1? And so let's assume, say, star, we assume the conjecture holds for all fields L with, say, GL isomorphic to GQ and transcendence degree L over Q is equal to 1, then I can show it for arbitrary K. So let now K be an arbitrary field with a Galois group of Q, say of transcendence degree greater than 0, because we have covered that case already, and assume if you take an element in K which is not in Q, so something transcendental, then we consider the relative algebraic closure of Q of x inside K, we call that L. This is a field of transcendence degree 1 over Q now, and you have from GK, you have the restriction map onto GL. This is onto because your L is relatively algebraically closed in K, and then of course you pass down to, again via the restriction map to GQ, then the composed thing by what we have shown in the lemma is an isomorphism, this restriction map, and that tells you that those two guys also must be isomorphisms. So in particular, GL is isomorphic to GQ, and we are in the situation here. So that means by the conjecture, by the assumption we have made, there is a Henselian valuation, call it W on L, with divisible value group and with residue field precisely Q. Now what does that tell you? That tells you that in particular this must be a non-trivial evaluation because the field is not Q itself, so there's a non-trivial evaluation, there's a non-trivial element in the maximal ideal, which means that there exists a non-zero, say y, in the maximal ideal of this non-trivial evaluation W, but what is this non-trivial evaluation? That is the intersection over all P of the valuation rings O sort of M, the maximal ideals, maybe maximal ideals of the VP tildes intersect L, where what is VP tilde? VP tilde is the coarsening of VP on K, which we have from the proposition here, is the coarsening, the relative rank 1 coarsening of the valuation VP on K, which you obtain by adjoining to the valuation ring 1 over P. So your valuation ring OVP tilde being OVP adjoint 1 over P. This is a relative rank 1 coarsening, again, hence again, then of characteristic pair 0, 0. And because we have this non-zero element in here, and because we are rank 1, we know this W is essentially, if you intersect it down to a finitely generated sub-extension of L over Q, which will be a function field of a curve over Q, it will be a geometric valuation. So we have this non-trivial element Y, which sits in all those maximal ideals of these corresponding coarsenings, which tells you that by choosing arbitrary elements in MVP tilde for a particular P, that they will also be in MVQ tilde for any Q. So you have to repeat, to apply star many times to get that you have that the maximal ideal of this rank 1 coarsening VP tilde is in fact the same as with respect to any other prime, VQ tilde. That means they are all the same. That means they come from one and the same valuation, and so the valuation V, which is just this VP tilde, and they are all the same, VQ tilde, is the valuation claimed to exist in the conjecture.
Could you explain again why MW is equal to this intersection?
Because this MW, this W is a characteristic 0, 0 valuation, and it is a coarsening of all the VPs. The restriction of the VP to L, they are mixed characteristic, and so that means it's something into the maximal ideal of this W is in all these maximal ideals of these coarsenings. That is just from general theory of coarsening of variations.
Why was there a coarsening of the VP?
Because if you take the VPs on K and you restrict them to L, they will be the corresponding VP of L's.
Oh, okay.
And then they all have that proper coarsening W, and that can only be the VPL tilde. You have to do a bit of work here,
Okay.
but it's not difficult. It's just straightforward variation theory at that point. So that means all we need to do is prove the conjecture for transcendence degree 1 over K. And now, question. Let's move towards the proof.
Sorry, can I ask something about the conjecture? When you say the residue field is Q, you really mean Q, not elementary equivalent to Q. When you say that there exists a Henselian valuation with VK divisible and the residue field is exactly Q.
Exactly Q,
Exactly.
not elementary equivalent. I will come to the elementary, so the model theoretic version of the conjecture towards the end of my talk, and I will then also say something about applicability to questions of Hilbert 10. How that can give us a new machinery for detecting whether or not polynomials over Q in many variables have or do not have Q rational points. Okay, let me just indicate a few ideas in the direction of the proof of the conjecture. We have two cases. So, of course, now for transcendence degree K over Q is 1, equal to 1. We have reduced it to that case, and so it suffices to prove that. Case A, we have all those mechanic valuations VP, and they may or may not induce infinitely many topologies. So KA is that the VP induce finitely many topologies. Okay, now in this case, they obviously can not all be rank 1. In fact, only at most finitely many of these VPs can be rank 1, because any two rank 1 variations are independent. If they are distinct, then they would induce different topologies. So most of them are rank 2, and in fact centered at only finitely many. So if you go to the corresponding VP tildes, only finitely many occur there, up to equivalence. Which means, in particular, that there is one such geometric valuation, which is the VP tilde for a large set of primes, namely a density greater than 0 set of primes. So that means, in particular, there exists an element x in K, obviously transcendental, such that if you denote by sigma plus of x the primes where this x has positive valuation, there must be an x, namely in the maximal ideal of one of these geometric valuations, of which we have up to equivalence only finitely many, such that this set has density, Dirichlet density. It always does have Dirichlet density, one has to do a bit of work here, but it has positive Dirichlet density. Now, using the Chebotayev, which we have proved in proposition C over there, that tells us that in fact this sigma plus of x, so this is using Chebotayev in a non-trivial way many times, you see that this sigma plus of x has to be all primes. So there is an element which is in has a positive valuation under all those VPs that can only be that is in this VP tilde for all the P's, and hence all the VP tildes are the same, again, for all primes, and that proves that is then the V we are looking for in the conjecture. So in this case we are done. We need all a bit more argument, but this is the rough idea.
So how did you get X from
so if I look at this, so the variations, if they induce differently many topologies, finitely many topologies, then there are only finitely made rank 1 variations, forget about those. And for the others, they come in bundles as to whether or not their VP tilde is equal or different, but they can only be finitely many VP tildes. So in one of those VP tildes, there must be infinitely many primes centered. And that is how you find that. And not only infinitely many, but density greater than 0 many. Because you're covering your primes, forget about the finitely many, you're covering your primes according to in which VP tilde they lie. This is a finite cover of almost all primes. One of these sets, and they are all of density something, one of these sets must be of density greater 0.
Is it clear that the density even exists?
Yeah, you have to work it.
Okay.
It always exists, and assuming under this finite many topology assumptions, it must be one of them must be of positive density, and then you apply Jotayev to show actually this cannot be other than this set being all the primes. Okay, this is case A. We are done with that. Case B is the one which is still open. So infinitely many topologies. And I can say a lot about this case. I will only say a few things. This is a very interesting case. So if a counterexample to the conjecture exists, it must be in case B, and it's a very interesting counterexample. It has properties which I think everybody believes to be just impossible. But I write some of them down. The first one is, in that case, we have that K satisfies what you may call the fundamental theorem of arithmetic. Namely, you have that every x in K is uniquely determined by its periodic values. Is uniquely determined by the family Vp of x, where P runs through the primes, including the ordering, so that simply means we have to say whether x is positive or negative, so the sign, plus the VPX's uniquely determine the x. So that is sort of the version of the fundamental theorem of arithmetic you have here. Another thing you have is that the intersection of all nth powers is just 1. The third thing which is happening, using the lemma here, that you have this isomorphism here, that tells you that for every x you have modulo n, a unique representative in the rationals. So you take, for growing n's, you take these representatives in the rationals, unique representatives in the rationals, and they will give you, as n grows, a sequence xn. So there is a sequence for each x. Okay, there is a sequence xn in Q, which is defined to be the representative of x modulo nth powers taken from Q via this isomorphism here. And it turns out that this sequence is a p-adic Cauchy sequence for every p.
The X is in K cross, or is it? Yeah, is it the same for P cross? I guess it's probably.
Yeah. Such that for each p, this sequence is a p-adic Cauchy sequence. It's easier if you take that, not taking xn to be the representative mod n, but rather mod n factorial, then you see more easily that this will give rise to a p-adic Cauchy sequence for each p. And what is the limit? The limit, the sort of, as n goes to infinity, but now p-adically for each p, is the residue of x. So let's say the Vp tilde adic residue of x in whatever that residue field is, it will be a subfield of Qp. So that is a very strong property, and that made me believe in the summer that this cannot be, because then all the local topologies will be the same, but this is not the case. You see, if you have these sequences, you can define a topology on K which says that two elements, x and y, are close to each other if they have a long stretch of the this sequence having a large initial segment which is identical. That gives you a topology on K, an interesting topology on K, which clearly is continuous with respect to multiplication. Unfortunately, it is not continuous with respect to addition. And that is the big problem here. So a lot of stuff entering here is multiplicative and not additive. Maybe in order to kill case B, we need some type of additive combinatorics, as we have seen earlier this week. I haven't followed up that line. Okay, a lot more things to say in case B. I will not list them here, but it's a very, very special field. So even if there's a counterexample, you have a very interesting counterexample, which probably is the counterexample to many other conjectures, but never mind. Let me move on towards the end just to another, I think I need more space, the relation of this conjecture to what is called the birational section conjecture in Anabelian Anabelian geometry, and that.
Sorry.
Yeah.
Maybe I'm confusing myself, but how the case A is even possible? Because VP induces like usual p-adic evaluations on Q, and they define all the different topologies on.
On Q, the p-adic evaluations all induce different topologies, but not on that field K here, where the V is non-trivial. If that V is non-trivial, then it has the same topology, it induces the same topology as all the p-adic evaluations. As soon as you have a composed, so a valuation of rank greater than 1, if they have a common coarsening, non-trivial common coarsening, they all have the same topology. That is why.
Oh, I see.
Why that is possible.
Can you say that again? I'm not sure I understood. So what? If the VP is induced. If VP induced this same topology on K as VQ, then when you restrict to Q,
They will no longer do it.
they will no longer have the same topology.
No.
Oh, okay.
No. Because you have infinity, if you are not in Q but in K, you have elements which are infinitesimally small. By being in the maximal ideal of the coarsening, that means it's closer to 0 than any rational, non-zero rational number. But still a non-zero number. Okay, birational birational section conjecture. Of Grothendieck's program of Anabelian geometry. Over Q. What does that say? That says if C is a, say, smooth projective curve, over Q, then any section say S of the canonical restriction map of the absolute Galois group of the function field of the curve over C, then to, under the restriction map here, the absolute Galois group of Q, any such restriction, any such section of the restriction map comes from a Q rational point. This is the section conjecture. Birational section conjecture comes from some point P, which is Q rational, which means that S of GQ, which of course gives you an isomorphic copy of GQ inside this big Galois group over the function field over GQ, sits inside the decomposition subgroup, let's call it D sub P. So this is the decomposition subgroup of the valuation, say, V sub, and now here's a capital P, nothing to do with our V little p's before that, because this is a rational point on a Q variety, on a Q curve, and not a prime. Decomposition subgroup of the absolute Galois group of our function field. And once you have that this sits inside such a thing, then obviously the fixed field of the decomposition subgroup is a Henselian valued field with respect to Vp, and then you move on to the fixed field of SQP, and that then has divisible value group and residue field precisely Q. So it turns out, via our reduction to, which I've just erased, to the transcendence degree 1 case, this birational section conjecture of Grothendieck is in fact equivalent to our Galois conjecture. So I've worked on this conjecture for quite a while until I discovered that actually this is an old conjecture, but only after you've proved this reduction step here. So of course, we have experts on the birational section conjecture in the audience. Jacob knows much more about that than I do, but I think it's interesting to see that these things are related. Let me, in the last few minutes, move on to a model theoretic variant of this conjecture. So the model theoretic version of the Galois conjecture says, do not ask isomorphism of Galois groups, but elementary equivalence. Now I should say what that means. Two profinite groups are elementarily equivalent, not if they are just elementarily equivalent in the language of groups, because that doesn't capture the topological properties. So the language you're looking at here is the language which is not talking about elements in the profinite group, but in finite quotients. So it's a many sorted language. You have lots of, for each size of the quotient n, you have a different sort, or up to n, and you can make all of this precise, and then you are talking about finite groups, and of course it's elementary equivalence there, together with the projection maps between the various dimensions, with the various sizes of quotients. So it's a bit elaborate, but well understood, goes back to Van Dries, McIntyre, Cherlin, Zoe Chatzidakis has written up a very nice account on that. So this is well understood. So we have that notion of profinite groups being elementary equivalent. What would happen on the right-hand side? Same statement, K should admit a Hanselian notation with divisible value group and residue field now elementarily equivalent to Q. So again, this consequence you would have, but it turns out that this model theoretic variant, you think that's probably much bigger than the other one, because here you are talking isomorphism and here you are only talking up to elementary equivalence, but there's an implication going here. So in fact, the model theoretic version is stronger. If you can prove the model theoretic version, the original version is a simple corollary. So the model theoretic version is a good deal stronger, essentially because you have to be effective in your way of detecting in particular the p-adic valuations. Here in the abstract sense, the original sense, you can just see them by talking about subgroups of GK. This elementary language of profinite groups is not talking about subgroups, it's talking about quotients. So you have to find bounds on how far, how big a quotient you need to have in order to see p-adic valuations, which is very delicate. Philip Dittman has done some work on that. It is doable, but it's difficult. You probably will not get this restriction being an isomorphism. Certainly not for free. So there's a lot of extra work to be done. Maybe it's just plain wrong, but this is the model theoretical version. It's nice because it would be, because we need all those explicit bounds, it would be more explicit, more computable, and then, I mean, the whole thing, the whole program of Anabelian geometry was launched by Grothendieck in order to reprove faultings in a proper way, meaning that he thought that via these sections you can Galois theoretically encode rational points on varieties, and you have Galois cohomology and a lot of machinery on the group side, which could help you detect those points. So that is the whole philosophy here. And so in particular, if you have the model theoretic version, you get more closer to explicit computations. But I think I should stop here.